Hi everyone, welcome to the next lecture, to today's lecture. We are picking up our discussion on convolutional neural networks. We are diving deeper into aspects of stride, padding. Actually, we likely won't be able to get to pooling layers today, but we'll basically develop a much more thorough understanding of what convolutional layers are and how to put convolutional neural networks together as building blocks of convolutional layers. All right, so just a quick recap from last time. Here is where we, looks like the top of my head is all that's visible. Apologies, let me just adjust this a bit. Here's a quick recap from last time. We're talking about convolutional neural networks. We're diving deeper into CNNs. We justified the need for CNNs and convolutional layers by saying that fully connected layers have a major problem. Fully connected layers do not scale to high dimensional data because as soon as you have every pixel as a particular dimension in your input, and if let's say you want to preserve the same number of hidden units, you can relax that assumption. But let's say you do, you very quickly realize that you run into a large number of parameters, 1.6 billion parameters in just the first layer. And that does not scale well to multiple layers and to even for a single layer, this just simply doesn't scale. So what we said was that if we can just make a couple of assumptions, those are in a lot of cases reasonable assumptions when you're dealing with spatial data. They are not perfect, they're not always true, but they have demonstrated their value across a range of applications. And those assumptions are, let's make sure that every hidden neuron is not connected to every pixel in the previous layer, but a local connectivity. So if it's not a fully connected layer, it's a locally connected layer. That reduces the number of parameters pretty quickly because now you don't have every single, this is not a full bipartite graph, this is a locally connected graph. So I is not connected to everything else. There's only 100 connections, and so that reduces parameters to 4 million from 1.6 billion. And the second assumption that we made was of stationarity or parameter sharing. That no matter what location we're looking at, whether that's center top or top right, we're going to share the parameters at all these locations, which immediately collapses from 1.6 billion, 4 million to just 100 parameters for this operation. And the reason why you might justify this is by arguing essentially what we end up arguing in the homework, that there is translation equivariance, that you want the computation or the features or the activations which are computed at the next layer to be equivariant, which means that when the input is shifted, the output is shifted as well. So notice that if these parameters were not shared, you would not get that because they are functions of locations. If they were functions of locations, then shifting would not result in shifting of the outputs. Now you have to ask yourself, is translation equivariant a good thing? Does my data satisfy translation equivariance? And turns out that across a range of applications in computer vision, when you're dealing with natural images which are unregistered, unaligned, you do not already know that there is, all objects have been perfectly aligned. It is a reasonable assumption. And that assumption can be tested by taking a data set, by not making that assumption, by making that assumption and seeing whether you get better generalization. And at least, in a lot of cases, that has essentially held true. Now, if you had data sets where you had images, but all the objects were perfectly well aligned, such that let's say it was a face data set and all the eyes were aligned and the noses were aligned, then I can see this assumption being harmful, because if your data is aligned, then there are statistics of top right versus bottom left patches that will be significantly different, and you want to pick up on this fact. You want to pick up on the fact that the weight here at the bottom left may be looking only for certain aspects of the chin of a face, versus the top right might be looking for something in the forehead. And then you do not want to share these parameters. But in general, for visual content, when you do not have this alignment, this is a fairly common assumption, and it is valuable. So these two assumptions led us to a natural operation of a convolution. It is that this weight W became the convolutional kernel or the filter. We went through a couple of different intuitions and formalizations of convolutions. We will not repeat them today. We will just repeat the actual thing that is implemented, where there is an output Y whose entry at a row comma column. So if you want to know Y's value given an X, which is of size perhaps N1 by N2, and a W which is of size K1 by K2. If we want to know the value of Y at a particular pixel, R comma C, we find that pixel in X, and we essentially place W at that location, and this element-wise multiplication, if you will, gives us this Y R comma C. And this element-wise multiplication does actually have a really nice intuition. You can think of it as X vec cropped out at R comma C inner product with W vec. So if you string out W as a long vector, and you string out you crop out a part of X which is cropped out at the R comma C value of the same size as W, and then you take an inner product between those, that's what is stored at this. And the reason why I'm writing this is to indicate something. This is inner product, so it means it's a linear operation. Convolutions are linear operations. You will prove that. And you can prove that in multiple ways, by this sort of an operation, by writing them down as a matrix multiplication, by writing them down as Toeplitz matrices or circulant matrices. And so it's good to remember that convolutions are linear operations, and so they will satisfy everything that you know about linearity, and so on. All right, so that's an illustration of exactly what I said. If we want to compute Y 0, 0, we place this filter at this particular location, do an element-wise product. When we want to compute Y 0, 1, we simply shift the filter over, and this sort of summations of A and B's gets you to this particular output. Okay. So this is the convolution operation. We're shifting filters, we're placing it at all of these placements. I want you to notice that at the very end, at the very end, we end up with this. There's one other placement where you place the filter at this location. I appear to be missing a slide, but notice that the input started out as 6 by 6, and the output is now 4 by 4, and this is by construction, because if you do not want to place your filter outside the bounds of the image, which you cannot, then you end up with something smaller because the filter has a specific size. This is a problem that we will cover later in the lecture today. We'll talk about padding, but just be aware that this particular way of placement of filters is called, this is a valid convolution, which means that the filter has never been placed outside the bounds of the input. If you do this in Python or MATLAB, you can specify valid as a convolution option, and this is the sort of outputs that you'll get. Notice that if all we had done was padded 1 pixel around the boundary of this thing to have 1 pixel padding all around, notice then we could actually have gotten an output pixel here, which would require, I should use color so that it's clear. If we want this pixel right here, then it would require a placement of your filter here. This placement, actually that's not true. One to the left, one to the bottom. So here, this would be the placement. Sorry. So at this placement, you can actually find a value here. And the way you would allow this placement is by padding all around by zeros. So you would at least be able to define this dot product operation. You would, the filter values would multiply 0 here, so they would contribute nothing. And so only these pixels would contribute into the convolution output here. But if you did that, you would get a output of size 6 by 6 as well through this padding. We will talk about the relationship between the size of the filter and the amount of padding required, but you can already see that there has to be a relationship. If you have larger filters, clearly you will need larger padding to get the same sized output. So the blue thing is a 6 by 6 output, and if you want the output of your convolution to be the same size as your input, typically in convolutional implementations, you will find a parameter same. So the same versus valid convolutions will give you two different outputs. Valid will give you typically a smaller output, smaller proportional to the size of the filter. Same will give you the same sized output by zero padding around the boundaries of the input. Okay, so So this is where we were. We'll cover we have to cover a few things today. So let's get started. The first thing we have to cover today is a particular analogy or a particular way of comparing fully connected layers and convolutional layers. Last time, so now where we are in this lecture is that we know what a 2D convolution is. We understand that very well. But how does that relate to how does that become a layer in a convnet? And that's what I want to look at now. So on the top, I will draw a fully connected layer. So on the top, it's an FC layer. On the bottom, it's a conv layer. And I will try to draw it similarly so that we can actually make a 1:1 sort of comparison. So an FC layer, let's say it starts with HL minus 1 living in RC1, and it ends in HL living in RC2. And we can visually draw this as we have been doing in the class by these sorts of nodes that we draw. They go from HL-11 to HL-1 C1. There's C1 of these, and there's C2 of these on the output side. So C1 of these on the input side, C2 of these on the output side. We are usually interested in this like ith neuron here, and we know that HLI is summation of j equals 1 to C1 HL-1j times Wij. This right here is a scalar product. And what is Wij? Wij's are these weights on, so between the jth neuron and the ith neuron, there is a Wij. This scalar is Wi1. This on this edge is Wic1, and so on. Okay, so far so good. We are well familiar with this sort of a layer. The reason why I'm writing it this way is because I'm going to make a 1:1 comparison to a convolutional layer. So in a convolutional layer, we have something very similar. We have T1 input neurons, which and the reason for C is very clear. These will start becoming channels, and we have C2 output neurons, the same as above. The only difference now is instead of H being a scalar, this H is now a two-dimensional matrix. Each one of these neurons is a two-dimensional matrix, N1 by N2. So on the top, HL-1 was a scalar. It was a one-dimensional value. You strung them together into a vector to get HL-1 as a vector. At the bottom, HL-1, the first entry, is not a scalar. It's a it's a feature map. It's a 2D matrix. It's a matrix of size n1 by n2. And that's what's happening for everybody. Let's say the output is let's say we're doing same size convolution, so the outputs are also the same size. We'll talk about the sizes in a bit. Don't worry about that. And this is the ith neuron. This is the jth neuron. Everything is a n1 by n2 sized filter. Now let's talk about the weights. As far as the weights are concerned, this weight on the edge, at the top, it was a scalar. Wi1 was a scalar. Now Wi1 is also a matrix. This is Wi1, which is a k1 times k2 matrix. Wij similarly is a k1 by k2 sized matrix. And along each edge on the top is a scalar, along each edge is a vector. It's a matrix. And now let's write down how we'd actually compute. This object is, I'm writing with capitals because these are matrices now, HL of I, so the ith neuron, the ith channel, as it's called in TNNs, it's an output similarly to the top. There is a summation over J, which is the number of input neurons or channels of HL minus 1I, except we will replace the scalar product by a convolution, a 2D convolution. And so this right here is on the top. Compare this equation, which computes HI, to this equations, which computes HI. There is a certain symmetry. That symmetry is, instead of multiplying and adding scalars, we are convolving and adding feature maps or matrices, right? And let's just, and our expression, if you want to write down the full expression, HL of I is a matrix, R comma C entry in that has a summation over J, has a summation over A, has a summation over B, which are the spatial summations that we've been doing, and it's HL minus 1, I, R plus A, C plus B, Wij, AB. So lots of notations, lots of underscores and like indices, but the high level stays the same. Every node or neuron or activation now has become a map. It's become a 2D object, and therefore, what do we do with 2D objects? We don't just we convolve two-dimensional objects and then we add them together across the channels. And so that's the 1:1, if you will, comparison of a fully connected layer in a neural network and a convolutional layer in a neural network. Another way of comparing them is in terms of parameters. So at the very top, at the very top, notice that the ith neuron, I can group together all these scalars. So all the parameters associated with the ith output neuron, I can group them together and I can call them the Wi vector, right? And this is what we've been doing. There's a W1 vector, and we've been using them as transposes to form a matrix. There's a Wi vector, and there's a WC2 vector, right? So that's how many of these vectors there are. So the total number of parameters has been C2 times C1, because there's C2 of these things. Each one is C1 dimensional, because that's how many input edges are coming in. So that's the total number of parameters on the top. Well, let's do that same analysis here. What does this object look like, correspond to every single output neuron I? Well, it's a 3-dimensional object now, because these are the parameters associated with the ith object, the ith neuron. It's a K1, it's a K1 times K2 times C1 object. This is a 3-dimensional tensor now, corresponding to the ith object. And there's how many of these? Well, there's C2 of these. Let me take a question. Since the convolutions are just dot products, we will have to unroll them somehow to get something similar to an FC layer. The tricky part seems to be the fact that every input doesn't contribute to every output. So notice that we are now talking about, so this operation right here, this I've already expanded out as a convolution. HI convolved with WIJ gives you a two-dimensional object back, and we're summing up a bunch of two-dimensional objects in this summation. So we don't have to do any unrolling. We will have, like, if you're implementing this in Python or C++, then you will have to take care of the unrolling. But conceptually, as a mathematical operation, convolution has been handled by writing this symbol. And so now the output of that convolution is a two-dimensional matrix that we're summing over. Okay. So there is so just to complete our thing, how many such parameters are there? Well, just like there was C2 times C1, now we have K1 times K2 times C1 times C2 number of parameters. That's the number of parameters in these things. The tricky thing in parameter calculation always is that people tend to forget the bias parameter, and I've ignored that here as well. If you want to incorporate the bias parameter, remember that every single output neuron corresponds to a bias parameter, and so really there's a +1 here, and there's a +1 here. So C2 output neurons, each one of them corresponds to a K1 by K2 times C1 plus 1 number of parameters. Okay, shouldn't the HL-1I be HL-1J? Thank you, that is a typo. Thanks for catching that. My bad. This is in fact a J. Yep, just like it is on the top. Thank you. Okay, so hopefully that gives you some intuition. If that was, that gives you a 1:1 analogy. If that was too mathy, don't worry. We have, I try to interleave math with pictures, so we have pretty pictures coming up. So here is the pictorial view of everything that we just talked about. We are going to write down a 32 by 32 by 3 image, which is the CFAR type images that you're going to be working with in this sort of a representation. So this is width, this is height, and this is the number of channels, which is R, G, and B as input. And what we are going to write down is this is now a filter. This is a 5 by 5 by 3 filter. Notice that the 3 is coming in because there are 3 channels in the input, and we just drew a picture and we made this connection that you have to have the first channel of this correspond to the R, G, and B. So this three-dimensional, when we go to convolutional neural networks, we have to generalize our thinking from 2D convolutions to convolving 3D objects. And so every filter is a 3D object, even though we may not always specify the third dimension. You will often find that people are saying that I have 5 by 5 filters, but they don't always talk about the fact that there is a third dimension, which corresponds to the C1 dimension in the previous layer. So this is the C1, this is C1 again, so it's the same size. And so this is something to keep in mind, that filters always extend the full depth of the input volume. That we place, that we do not perform any sliding of the filters in the channel dimension. We only perform sliding of the filters in the spatial dimension, just like we've been showing you in the 2D convolutions, which is why you can think of this as multiple 2D convolutions summed up together, or a single 3D convolution, like this entire 3D tensor being moved around. Could you please explain conv2D and conv3D? So that notation of conv2D and conv3D is actually slightly overloaded. There are 3D convolutions as well, where you slide in the temporal dimension, but let's keep that aside. As far as we are concerned, for dealing with images in this class, when we say conv 3D, what we actually mean is exactly what's on your screen right now, is that you do not have just a n by n object as input. You have a n by n by some C1 object. So there is a height by width by C1 input. There is a K1 by K2 by C1 filter or that is convolved with this. And the convolution is really it requires that the filter be slid over the image spatially. And by sliding, what I mean is you place this filter down at a particular location. That location, you do an element-wise product, just like we've been talking about. This is conv 3D because there is a third dimension as opposed to just 2-dimension that we're doing element-wise product. But really, it doesn't matter. As far as element-wise product is concerned, you are taking chunks of 5 by 5 by 3. This is a 75-dimensional dot product. So just like the X vec and the W vec I mentioned, this is the W vec and this is the X vec extracted at this R comma C location, right? If this right here is the R comma C location. And instead of extracting out a 2D matrix, we're extracting out a 3D tensor and elongating that into a vector, and then adding, of course, a scalar bias. And so this gives us a scalar right here. When you move this placement over all R comma C locations, you will actually get a object, an activation map or an output, which is in this case 28 by 28 by 1. Why is it 28? Well, because you cannot place this 3D object outside of the bounds, and that's why, because it's there is some size of 5. We will teach you that relationship of how things shrink. You actually get something that's slightly smaller than 32 that we started with. So if the third dimension does not match, it is a 3D convolution. And just like we shift along the first and second dimensions in 2D con, we also shift along the third. Yes, that understanding is exactly right. And this typically happens in activity recognition, when you end up with videos of things where, let's say it's an intensity video, because RGB videos are actually 4-dimensional tensors, but let's say it's just a grayscale video, then you actually have a 3D object which is height by width by time, and then you may have a filter which is some spatial dimensions by time dimension. The third is a time dimension, and then you actually perform sliding in the third dimension as well. I didn't want to get into that because we're just meeting convolutions now. A lot of people are seeing convolutions for the first time. They're seeing 2D convolutions for the first time. So let's hold off like 3D convolutions for a while, and let's just try to understand. No sliding in the third dimension. We're still doing just spatial sliding. We're just sliding these tensors, which are 3D tensors, as opposed to 2D. Okay. So these things are called both activation maps. They're sometimes called feature maps. These things are called filters or kernels, weights, parameters. This is everything that we are learning. This 5 by 5 by 3 filter, and this is what we will be producing and visualizing. Why does the activation map have depth 1? Excellent question. Why does the activation map have depth 1? Because so far we have only talked about one 5 by 5 by 3 filter. This 5 by 5 by 3 filter, there's only one of them. It is placed in the third dimension to match, and you place it at all spatial locations. It will only give you one channel as the output because there's only one filter. However, you are not restricted to have only one output channel. If you want multiple output channels, you need a second 5 by 5 by 3 filter. I've illustrated this with green, and the previous slide it was illustrated this with blue. So when you have a second 5 by 5 by 3 filter, you convolve it at all spatial locations. You get a second 28 by 28 by 1 channel output, if you will. And that's exactly why we need to have multiple of those. So in practice, we will have these 5 by 5 by 3 objects. So, and we will have multiple of such objects. How many such weights or tensors or filters will we have? Well, that's a design choice. It's up to you to decide. Just like in fully connected neural networks, you decide how many neurons you want in each hidden layer, and that directly determines how many parameters you have to learn. It's the same thing. It is up to us to decide what C2 here is. How many such things do we want? If you want 2, if you want 10, if you want 20, that's an architecture design choice. So for example, let's say we were to pick that I actually want 6 of these. So I decide that it's a convolution layer with 6 filters. Those filters are all of 5 by 5 spatial resolution. Sometimes people will just say, I have 5 by 5 filters, 6 of them. They will not specify that there is a third dimension of 3 because it's clear that you can read that up from the previous layer. You do not have flexibility in choosing C1. You know that each of your filters has to have the third dimension equal C1 because it has to only shift spatially. So if you had 6 5 by 5 filters, you get 6 separate activation maps. On what basis do we decide how many filters to use and what is the size of the activation map stack? Excellent question. And do you remember the joke from, I think, L2, where how do you pick K? There is no basis. This is an architecture search problem. Whatever works is the right answer here. Usually people have practitioners' intuitions. Usually you will find architectures that have certain patterns. The exact numbers are under-specified, but the patterns can be picked up on. Usually for image classification type architectures, what you will find is that the number of channels go up. So you start with 3 and maybe you'll end up with 6 and maybe you'll double them 6, 10, in powers of 2, perhaps you'll go 8, 16, and so on. And usually spatial resolution goes down. So notice in this 32 went down to 28, which went down to 24. And so spatial resolution goes down. And that's very common in image classification type architectures. Let me see. Yeah, I have a picture of that. So in image classification architectures, you start off with 3-layer channels and high spatial resolution, and you will typically end up with small spatial resolution and high channel dimensionality. At some point, the spatial resolution will be small enough that you will convert it, and we will talk about how you'll do that, into just a fully connected layer, which is then ultimately giving you the score for each category and so on. This is very common. This sort of a design, increasing channel dimension, reducing spatial dimension, is very common in image classification architectures. If you want to, on the other hand, want to perform pixel to pixel type transformations, perhaps you want to go from RGB to depth. You want to train a monocular depth estimator, or perhaps you want to train semantic segmentation. You want to label every pixel with the category. For those types of architectures, you want to retain spatial resolution. Your output ultimately has to be, in the end, something that is the same size as the input. So there has to be a height by width, and perhaps there have to be the number of outputs equals number of classes. Then there are a second part of the architecture that learns to increase spatial resolution. Those are called transpose convolutions. We will talk about them later in this class, but for now, let's just take it one step at a time and understand CNN as well. Okay. I understand what filters do, but I'm not sure how they allow us to solve, for example, image classification and object detection. Any intuition that could help me? Give me 2 slides. I'll show you pictures, and hopefully that will build intuitions for what these filters are doing and how they help you detect objects. So this is what a stack of convolutional layers look like in a convolutional neural network. Okay, sorry, I'm just checking. There was a refresh of my questions at mine. This is what a stack of convolution layers in a convolutional neural network looks like. Notice that convolutional layers also are like in a lot of papers when you read, people will specify, I have this convolution followed by this convolution followed by that convolution. Even if it is not specified, typically there is a non-linearity in there. After convolutions, you are doing a ReLU. So every pixel, you do 0, max of that max of 0, that pixel value. This is exactly why the linearity of convolution, understanding the convolution as a linear operator help. If convolution is a linear operator, then stacking two linear operators means that the output is still a linear operator, which means two convolutions with no non-linearity in between them could have been represented by a single convolution. So just like you do not have matrix multiplication, that's just one matrix multiplication, you between two convolutions have to have this nonlinearity, otherwise it's just one convolution. And so there are ReLUs in between. Interestingly, the way convolutions are actually implemented on GPUs is not via FFTs or the butterfly method that a lot of people may have heard of from the signal processing background. The way convolutions are actually implemented on GPUs is, so this is the height by width by 3 object, and these are the placements of the W locations. So you basically go to every single placement. You take a patch of X. So this patch right here is the X vec at the R, C location. You string up that patch and you put it as the row of a particular matrix. So notice there is a lot of duplication in this matrix. Every row of this matrix is basically going over all possible placements spatially, cropping out a patch and storing it in a row. So there's lots of duplication. Memory is being wasted. But this is what is typically known as an IM to call operation. Notice we're actually storing this on rows. You'll see the column happen in the next slide. But pieces of X are stored there, and all of the filters or the kernels are stored along the columns. And this matrix multiplication, input matrix by kernel matrix or filter matrix, this matrix multiplication is computing all of the dot products of all of the convolution operations required in parallel. This is known as generalized matrix multiplication, and most GPUs have an API. So for example, CUDA APIs provide that as generalized matrix multiplication implementations. This is why GPUs made a significant difference in acceleration of convolutional neural networks being really used in practice a lot. Because of massive parallelization possible, which is required for the convolution operation. So this is how convolutions are actually implemented. But you won't have to worry about it. You'll make a call to a PyTorch library or whatever, or TensorFlow library, and this is what it's doing underneath. All right. So that is what a convolutional neural network is. A convolutional. At this point, we have told you what a convolution, 2D convolution is. We've told you how to do that for 3D objects. We've told you what a convolutional layer is. And we've told you that you can stack together convolutions in a convolutional neural network, just like you can stack together fully connected layers in a fully connected neural network. You can stack together convolutional layers in a convolutional neural network. Can you explain again why GPU wastes memory? It is not that GPUs in general waste memory. This particular construction of the input image is wasting a lot of memory, because if you think about it, everything on this picture has no overlap between the patches. But if there was an overlap, which there typically is, because you shift the filter one step over, then there's just one pixel left, and then K1 minus 1 pixels are exactly the same. They are pasted again in another row. Then you shifted one over again, and they're pasted in another row. So instead of storing the pixels once, the pixels are repeated over and over again in different rows of this matrix. So from a memory perspective, you are using more memory, but it's more efficient because then you can do this matrix multiplication in parallel. Are the terms kernel and filter used interchangeably? Yes, you will see kernels, filters, weights, parameters. Where weights and parameters are more general because that's more general in machine learning, but kernel and filter are used interchangeably in this context. By the way, kernel is also overloaded. If you use the word kernel, if you hear the word kernel trick, that's talking about the kernel function, not the same meaning as a filter. Okay, so that's where we are. We now have convolutional neural networks, and typically what will happen is that we will stack convolutions and rectified linear units and convolutions and rectified linear units. There'll be a layer called a pooling layer, which we will teach you about, and that will typically convert these activations into giving us values for categories. So just like we were doing with CFAR dataset with fully connected layers, with convolutional layers as well, we will try to predict these categories. Let's take a look now at the kinds of questions we were getting. What are these filters learning? What should we think of them? So this is layer 1 in a CNN. This is our image. It's height by width by 3. This is the input. This row right here, these are 5 by 5 filters, 32 of them, right? So each one of these is 5 height by 5 width and 3 channels, obviously, because it has to match the 3 channels of the input image, RGB. Because these 3 channels multiply R, G, and B, we can visualize these parameters as images as well. We can only do this for the first layer, but at least for the first layer, we can just IM show them. We can visualize them as images as well. So there's 32 of these that we are visualizing. That's what the parameters are. We have already learned them. We have learned them by doing this W star is equal to min loss of W over your data set, right? We're going to do gradient-based learning and all of that, but let's say somebody comes to you and say, I've already done my learning. Here's what I find. These are activations. These are the outputs of these convolutions. There's 32 of them as well. Why are there 32? Because there are 32 filters, right? So for each one of them, we have those activations. So this height by width by 3 object gets convolved with the first one to give me this activation. The second one is here, the third one is here, and so on. And the visualization that we're looking at in the activations is that whenever there is high positive values, they are visualized in the activations as white pixels. Whenever there's low positive, they're visualized as black pixels. And so the interesting thing here is if you just stare at this, what does this filter look like? This filter is placed at all spatial locations of the image. You take a dot product and then you store a scalar. This filter appears to be looking for a red blob at the bottom left. The filter has a red blob. So remember our visualizations from linear classifiers. Linear classifiers were templates that we could visualize. These are patch templates. They're patch level templates. And this particular template has this structure where there's a red blob here, red blob. And if you think about it, what is happening is that when you place that filter, when you place this W at this location, so this filter at this location, what you're going to get is that reddish blob is going to multiply with the orangish input that we are seeing at that location. And therefore, at this particular value, we have high positive values being stored. So it's a red blob detector that is firing at that location in the top left. And so these are our activations at the end of the first layer of the CNN. Let's see. Just to be clear, filters are the ones on the top, feature maps are the gray ones on the bottom right. Yes, that is correct. No other question. Not seeing any other questions. Okay. So that's a visualization of the first layer. Now, immediately we run into a problem because we can only visualize these filters for the first layer. When we go to the next layer, because for the next layer, what do features for the next layer look like? Well, whatever those parameters are spatially, if they are 3 by 3 or 5 by 5, in the next layer, C1 is 32. Why? Because C2 for this layer is 32. So you have 32 dimensional, let's say 5 by 5 filters in the next layer as well. Now that cannot be we cannot IM show 5 by 5 by 32 dimensional channel. We just don't know how to visualize that, and we don't know what these 32 dimensions correspond to in this layer. So this is a visualization of layer. Why is this misbehaving? The visualization of layer 2 weights, right? Layer 2 weights cannot be visualized easily. That's what I'm trying to say here. Okay, so in order to visualize that, we will resort, on the other hand, to finding we will have to develop new techniques for visualizing. This is a set of techniques that we will teach you in lecture 13. So ignore for now. These are visualizations. Ignore for now. These are called xylophogus visualizations or deconvolution visualizations. Ignore them for now. But what I'm showing you here are every 3 by 3 patch here. This is a wonderful figure from this xylophogus paper. Every 3 by 3 cluster of pictures here corresponds to a particular neuron or channel at layer 1. And what I'm showing you are the top 9 images in your data set that or crops of those images from that data set that lead to the highest activation. So basically, I go to these sorts of activation maps, I search over all pixels here, and I find out where are the large positive values showing up. And at those locations, I go and I crop corresponding images to find out. So I would crop, for example, this light of this headlight of this car image, and I would draw that here, right? So this tells me what are the input images that lead to the highest activations at this particular layer and at this particular channel at any pixel spatially. And so by visualizing that, I'm asking the question, what kinds of images does this neuron or this channel like? What does it fire? What does it respond to? Okay, so for layer 1, when we visualize what are these patches in the input that lead to the highest activations, what we find is that there are certain neurons, for example, this one just seems to look for orangish tones or hues. This particular one seems to look for yellow patches. This is a particular texture. These neurons tend to either look for simple shapes, simple colors, or textures. When you go to slightly higher layers, so this is layer 3 in a neural network, what you find is that now more sophisticated patches or more sophisticated objects are building up. So this particular neuron, this 3 by 3 clusters, the top 9 images, these all look like they are all crisscross patterns in the input that this neuron is responding to. Every time it sees a crisscross pattern, there is a high activation in this channel somewhere in spatially. These seem to be responding to circular objects. Every time there is like a wheel type thing, it responds. This tends to be responding to looking at torsos of humans. Notice this is just me looking at them and trying to provide meaning to them. There is no ground truth to this. There is no programmatic way of checking this. This is visual interpretation, and so we have to be careful. It may be that I'm overreading into 9 images, and maybe that's not the full story. Why are the activation maps after one layer gray? So these activation maps, I imagine you're talking about them. Why are they after layer 1 gray? This is just a way of visualizing those channels. Every single channel in the output is a 2-dimensional feature map, and we are just visualizing them in a grayscale way. They are continuous values, obviously, and you can't have RGB visualizations because we're visualizing one channel at a time. But how are the filters different from the weights? Don't we learn the filters? The filters are the weights. So we're learning filters or the weights. Filters are not different from the weights. Okay. So this is what layer 3 looks like. And this is what layer 4 looks like. Notice now these cluster of images tend to be object parts. They are getting much more semantic. So there is a neuron that always appears to fire on dog faces. And that right there is very interesting because this is a data set of image classification. We have no annotations of object parts. We have no annotation of even object bounding boxes. So the fact that there is one neuron in there in your neural network that always appears to fire on dog faces is an interesting emergent phenomena. These visualizations, by the way, are looking at what parts of the patch cause most impact. So you can actually tell foreground versus background within the patch. Again, we will teach you how these grayscale visualizations are computed, but ignore them for now. But it's nice that there is like, round objects like cakes, there's like object parts, and ultimately even more sophisticated, dog face heads, bicycle wheels, and so on, that completely emerge. So the fact that part detectors and object detectors emerge in neural networks trained to just simply output the category of an object present in the image is a fairly interesting emergent phenomena. Okay, we're at time. All I'll say is that this is what we mean by learning features in a convolutional neural network. That there are low-level features that are learned in the first few layers. There are mid-level features and there are high-level features. Again, these visualizations, we will teach you how to compute. You will compute them in homework 3. But it seems like that these features tend to pick up on patches and colors and statistics, object parts later on, and they become more semantic. And that is an interesting phenomena in CNNs. And we will pick up on stride and padding and other things next time. I'll stop.